Okay, so this is our first meeting since the going over the course outline. The main purpose of these meetings are to communicate to you anything that you need to know, and also to give you a chance to ask questions because you're doing the lectures online. You obviously can't ask questions during the lectures themselves. So what I'll do to start is I just want to go over assignment one, which is now on the website. So if you are sitting in front of a browser, you can open it up, or you can watch my screen, which you should now be able to see. Okay, so assignment one will be due in 2 weeks from today. It's a very simple assignment because in terms of the course content, we're still going over preliminaries, and you haven't even seen Bitcoin or what's called the blockchain, which is the underlying data structure. We haven't even got there. And so so assignment one is pretty cool. And 2 weeks from today. In terms of when it's due, if you've taken a course with me in the past, you'll know about this, but what I do is I offer a slip day. So slip day is where you could miss the deadline for one assignment. So in this course, you only have 2 assignments. So your slip day you can use on assignment 1, or you can use it on assignment 2. And the assignment will be due, in this case, I just made them due on Tuesday. So it'll be due like in class kind of. And if you want to slip, instead of handing it in on time, you can hand it in by Friday that follows the Tuesday. So it gives you several extra days to finish the assignment. You don't have to tell me that you're using it. You just, if your assignment comes in on time on Tuesday, then I'll assume that you didn't use it. And if it comes in late for assignment 1, then I'll assume that you did use your slip day. And then the only rule is that if you use your slip day for assignment 1, then you can't use it for assignment 2. So for assignment 2, you'll have to hand it in on time. And if you hand in assignment 1 on time, then you might as well use your slip day for assignment 2. Okay, so this will just give you a little flexibility. I know your schedules sometimes get busy and things like that. Please put it in a PDF format. So no handwritten assignments, typed assignments, and then in PDF format, not a doc file or something like that. To give it to me, what you're going to do is you're going to use a system called EAS. The link is here. EAS is a system that's from engineering. So you'll log in using your ENCS or your Gina Cody username and password. So this is maybe different than your Concordia password. If you are a student in Gina Cody, you should have access to it. If you're not, if you're in a different faculty or a different university, then you will have to you'll have to get access to the system. So you can just submit a ticket to IITS and ask for access to it. So through here, I understand that they'll give you access if you need it. It looks like you have to log in here as well, but this is with your Concordia account, which hopefully you all have. Okay, so that's the EAS system. I will ask you what assignment to put it under assignment 1. If you change your assignments, like say you realize there's a mistake or something like that, it's still within the deadline, then you can just upload it over top, and we'll mark the one that comes in the most recent submission is the one that we'll mark. If there's any problem with this, you can always just email it to me just to sort of timestamp it. But I will insist that you eventually get access to EAS because we will send your marks back to you through EAS. Okay, so the assignment itself is just a written report. It's just you do a little research, and since this is a security department or program that this course is offered under, you can focus on security issues. So what you're going to do is you're going to do some research on, you can look at Bitcoin, you can look at Ethereum, you can look at what's called DeFi or decentralized finance, you can look at NFTs, cryptocurrencies, blockchain technologies, anything that's in that sort of cluster of technologies, you'll see that there's lots and lots of attacks that happen in the real world. Okay, not just theoretical. You know, people lose money, people lose other things, lose access to things. And so the idea for the project is to just search around, see what you find, and try and find something that's interesting to you. And then I want you to research it and just write a 3-page maximum. And once again, templates don't matter or anything like that. You don't need a title page, just, you know, assignment 1, your name, student number, and then your 3 pages, including citations. You don't have to have citations, but I assume that you don't know about these incidents off the top of your head, so you must have read about them somewhere. So I would expect that there would be some citations. The citations don't have to be to the academic literature. They can be to news articles and that type of thing. Okay, and this is an individual assignment. And so what I want you to do, and part of it is the project that, or sorry, the topic that you choose, the exact incident that you choose. Make sure there's enough technical depth there. Okay, so I want some technical depth on security, and then describe basically what happened, what the technical details are. So in this case, you might have to dig a little deeper than the news article. The news article might have kind of a surface level of what happened, and then you might have to dig a little deeper to figure out, you know, what actually happened. You can talk about the impact, you know, so what happened, like, was it a big deal, small deal? How many people did it influence? Did people lose money? Who lost money? That type of thing. And then was there a fix? Or how do we make sure that this isn't going to happen again? Did Ethereum have to change? Did, you know, whatever the case may be, okay? And so you can also sort of zoom out and say, okay, was this something that like people should have seen coming, right? And if they should have seen it coming, like what kind of went wrong? What were the preventative measures that they could have used to stop it before it happened? And are there any broader security lessons that we can learn from it? So is this a blockchain specific thing? This type of, you know, incident would only ever happen in this setting, or is it more of a general security thing? And so you would look for these kinds of incidences in sort of the broader space than just cryptocurrencies and blockchain and Bitcoin and that type of thing. Okay, cite everything that you use. Remember, you can't copy text even if you change the grammar. So you have to say it in your own words. You can take the idea from somewhere and then cite it as being, as I got the idea for this from this source, and then tell me in your own words what that idea is, okay? Citations can be informal, meaning like, I don't care about the format. You know, you can just say, I read an article and it, you know, it said this, right? And then say what the article said. Okay, so that's like almost like we're having a conversation. We're just talking. You don't have to write in a very formal way. Concordia's plagiarism policy, we went over that in the course outline, but you can double check with that if you need to. And yeah, in the course project as well, it's the same sort of rules around plagiarism. And we spent a lot of time last time talking about it, so I won't go over that again. Okay, so that's assignment 1. Is there any questions about this? So someone asked, do we have to write about real attacks or concepts? So conceptual attacks are fine as well. So if there's some theoretical attack that's proposed in the literature, like the example was 51% attack, that's fine. Now, 51% attack actually did happen in real life. So Bitcoin Cash, for example, which is a fork or a spin-off of Bitcoin, there were 51% attacks. And so a lot of these concepts you can probably find examples of, but you know, for example, there's some attacks that will happen only in 100 years when Bitcoin stops producing new Bitcoins. Like, we haven't got to Bitcoin yet, but if you know a little bit about it, you'll know it's a currency and that the supply is capped. So that would be like a purely theoretical attack because we haven't got there yet. But anyways, the short answer is yes, you can write about theoretical attacks as well. Other questions, just feel free to unmute and ask away about the assignment, and then I'll start taking questions about other stuff. Okay, yeah, take a look through it. Let's see. It looks like we're going to meet next week anyway. So ideally, we would have met last week, so we would sort of meet every other week. The problem is I had a commitment on January 25th, so that's why we delayed to this week. But I do have it penciled in a meeting next week as well. So if you have any questions about the assignment, try and work on it a little bit this coming week, and then you can certainly ask me questions next week. Next week's lecture will be in person, so it will be in Faubourg. I don't know if I have the room number. It might be on the. Yeah, it's in FGB 40. So in Faubourg, in the basement, Faubourg. So we'll occasionally, basically, when there's an asterisk, we will meet there, and it's the same format. We'll just have question and answer. I'll try and make a recording of it, so if you miss it, you have a chance to watch the recording. Okay, there's another question in chat. Just give me a second to read it, and then I'll answer it. Okay, so the question is sort of, how do I find these attacks when they occur? If I Google things, often it brings up like lots of crypto trading, these are the tokens you need to buy and sell and all of that type of stuff. And unfortunately, that's sort of what the space has become. So what you need to do is you need to, there's a couple ways of doing it. So you can just sort of improve your Googling skills in order to improve your Googling skills, like to include like security related terms so that you try and eliminate all of that other stuff. Another thing is if you can try and find a high level, like a kind of attack. So this might be a little harder to do, but if you can drill down and say like, I'm really interested in front running or minor extractable value, then if you put those search terms on, then right away you'll start finding like security things. Social media has a lot. So there's a lot of things on like Reddit, Hacker News, Twitter, like those kinds of things. But you need to know the right people to follow in order to kind of see them. So I agree with you. Like part of the challenge of this assignment, I guess, is to sort of get a toehold into where you find out all the different security incidences. I've seen like spreadsheets and things like that where people have, especially for DeFi. So DeFi is finance running on Ethereum. They've tried to like make a big list of all the different events that have happened. So I don't even know like where that is. Otherwise, I would give you the link. But if you Google around for that type of thing, you can find it. So, anyways, I don't have much good advice beyond that. Just try hard to Google, and if you can get a broader sense of what you want to look at, and then start, including that in your search terms, you'll sort of narrow down into the actual attacks itself. And if you have any trouble, you can always ask me as well. Yeah, and then the student notes also that the books are kind of old, which I agree with. And so, yeah, if you want to do something that's new, it's more like Medium, Twitter, like those Reddit, those kinds of places are where you would find the newer stuff. Usually, like people, sometimes they put it on Twitter, like they'll live sort of tweet an attack as it's happening. And then Medium's actually, it's kind of like a longer form for Twitter, for blogging, and there's other blogging platforms as well. So it's not just Medium, but that's where you might find a write-up that's, a page or two about a particular attack. So that's a good place to start looking as well. Okay, someone asks if all the lectures will be in person or just the ones that are asterisks marked. So first off, the lectures are online. So the lectures are on YouTube. So that's the lecture portion. And then we only occasionally have question and answer, which will be in person, which are the stars. So yeah, so you only have to show up to class or here for today, but going forward from today, you only have to show up to class if there's an asterisk beside the date. And when you show up to class, it won't be a lecture. The lectures are already covered in YouTube. It will only be either question and answers or talking about the assignments, or sometimes we might show you a demo or show you how the like software works. Like later we'll get into some of the developer tools and things like that. So that's the kind of stuff that you can expect during those sessions. Okay, there's a question about the content of the lecture. I will answer that, and I'll take questions about the lectures in a second. But right now we're just focused on the assignment. Do we write about one specific incident or a general concept? So it's up to you. You have a lot of latitude. Like, I just want a report that's interesting. I won't read it. The TA will read it, but it needs to be interesting and just showcase that you've spent some time looking at this. You're starting to understand the concepts and you can explain it. So if you think that like a more general kind of attack, maybe a theoretical attack, is the best thing and most interesting to you, and you can describe it and make an interesting report about it, then go for it. If you want to do like a blow by blow of a exact incident, like on this date at this time, this is what happened, though that can be really interesting as well. So it's completely up to you. Try and pick something that you're actually genuinely interested in, and then hopefully your report will reflect that. There is a marking guide for the report, grading. It's very similar to the project, but it basically, yeah, just I want to see some technical depth. I want to see what the impact of it is, and once again, these can be more theoretical. So it is kind of written in terms of a specific incident, and then I just want something that's interesting and it's clear and logical and things like that. It's written in a good way. Okay, other questions about the assignments? Any questions about anything other than the lecture material itself? Okay, so now I'll take questions about the lectures themselves. So there's a question about Schnorr zero knowledge proof. So I'll start there, and you can think about other questions you have. You can either drop it in chat, or you can just unmute yourself. So the question is, can I explain Schnorr zero knowledge proof again? This is covered in lecture 6. And so I'm just loading the lecture notes because it's the entire course. It's a big file. It takes a while to load. Okay, so the notes aren't split up by lecture. Maybe it's something that would be more convenient, but I'll just try and scroll to the right spot. Okay, so we talk about hash functions. We talk about digital signatures. And the zero knowledge proof is very brief. So what I want you to understand is sort of the high level concept of how it works. You don't have to understand the math. I don't even show you the math, but just be aware that there are these things called zero knowledge proofs. So the idea of a zero knowledge proof is I want to prove something to you without revealing it, okay? And usually what I have is I have, let me give you a concrete example, an example that's often used. Let's say I have like a driver's license and it's a digital driver's license, okay? Or think of it like a vaccine code, that QR code app or something like that, okay? And so what I have is I have this document and I have my name and I have my birthday and whatever. And because I care about privacy, it's encrypted. So if you pick up my driver's license, you have no idea what it says. There's a bunch of ciphertext there, okay? Now, that's kind of useless. If you have a driver's license that doesn't tell you anything about the person, how do you know what is written there? If it's encrypted, you don't know what's written there. And so imagine a world where, say, the government, they know what's underneath the encryption. So they know the plain text is Jeremy Clark and my birth date is whatever. And so what they do is they encrypt it so you can't tell what it is, and then they sign it. Okay, so they're saying that this is an encryption of my name, and it is actually my name. Okay, this is an encryption of my birthday, and it's actually my birthday. We're signing off on the fact that we know that it's your birthday. Okay, so I have this driver's license, and let's say I want to prove to you that I'm over 18 because I want access to buy alcohol. Okay, so I have this driver's license. The easiest thing I can do is I can decrypt it. So if I decrypt it, then I reveal to you my full birthday, which is more information that I strictly need to reveal. Okay, so what I could reveal instead is, imagine if I could prove to you that there's a year or a date and a year that's under this encryption. And if you were to see it, you would understand that it's more than 18 years ago at this date. If you, so that's essentially it. So what I'm doing is I'm proving to you a statement. Basically, zero knowledge proof always consists of, there's a statement to be proven. There's some information that's hidden that you want to stay hidden at the end of the protocol. So in this case, it's my actual birthday. And then there's something that I'm proving about that. So instead of an alternative of revealing that entire value is I just prove to you that it has a certain property. And that property is less information than revealing the full thing. So I know this is sort of vague, and zero knowledge proofs aren't that important. They're more important if you do certain projects in certain areas on blockchain. You could encounter them very quickly, but they're not part of the core protocol. With one exception, which is that you saw signature algorithms, and actually signature algorithms are built from zero knowledge proofs. So these are details that you could learn in 6110 if you took it. So anyways, the Schnorr zero knowledge proof is a very specific zero knowledge proof for I'm showing you the encryption of something, I'm going to prove to you something about it. Okay, so in this case, what I'm doing is I'm showing you my public key. And my public key is kind of like an encryption or a commitment to my secret key. It's not exactly that, but it's close enough that for the sake of this course, just think of it that way. So when I show you my public key, it's kind of like an encryption of my secret key. And what I want to do is I want to prove to you that, hey, I actually own this public key. Okay, this is my public key. I control this public key. Okay, and so in order to prove it to you, there's a couple things I could do. For example, if it's a signature key, you could say, okay, if that's really your key, I want you to sign this message. So that actually turns out to be something that you see a lot in the blockchain space. So you'll go to a website and we haven't gotten there yet, but your blockchain is basically your public key. Your address for receiving money is a public key. And the website will say, hey, I want to know that you actually control this public key. It's really your address. And so what they'll do is they'll give you a message and they'll say, sign it. And your software, you don't do anything, but you have to click a button that says, okay, I'm going to authorize my software to sign this. Okay, so that's one way that you could prove that you know how to use it. Now, another way is with the Schnorr zero knowledge proof, which does even less. So in that case, it's a little dangerous to go signing messages because maybe the message I ask you to sign is something inflammatory that you wouldn't want to sign, or maybe it's a transaction that send $1 million from your account to my account, and then I'm like, oh, this is the test message I want you to sign, right? So you have to be careful about what you sign, and you don't want to just go signing everything. Okay, so with the Schnorr, it's even less information. You don't even have to sign anything. All you're going to do is you're just going to prove that you know the secret key that corresponds to this public key, and then that's it. Okay. So anyway, so there is a protocol for doing it. Inside of it, there's a hash function, and if you toss the message into the hash function, it turns into a signature. So if you want to think about like because we didn't talk about signatures, you don't know the details of it, but if you want a mental model for how a signature works, it's basically a zero knowledge proof that here's a public key. I know the secret key that corresponds to that public key. Okay, and I'm stapling that proof to a message. Okay? So it's basically, here's a message, and only the person who knows the secret key is able to staple these two things together. Therefore, they sign it. So that's sort of what a signature is. So anyway, so Schnorr signatures and DSA or ECDSA, which is DSA over elliptic curves, those are the signature algorithms that you see most often. You see it in Bitcoin, you see it in Ethereum, and they're related to the zero knowledge proof. Okay, so anyway, that's a lot more information than you need to know, but the point of this is just to give you some intuition, so you're not scared off when you see zero knowledge proofs pop up. If you start reading about like snarks or Zcash or like a few different topics, ZK rollups, these are topics in blockchain where zero knowledge shows up. Okay, other questions? Once again, just feel free to unmute or drop it into chat. I'll warn you that it's easy to fall behind with these. I know I was a student, and because they're all recorded, you might think, oh, I'll just sort of, I'll do it. I'll look at them all reading week before the midterm. I think the midterm's after reading week, and so. But anyways, I really encourage you to try and keep up with the lectures and watch them sort of on a week by week basis, so that you can, some of the ideas they take a few, they take a few days to sink in, and everything kind of builds on each other. And so if you have questions about one of the earlier concepts, it gets harder to understand the concepts that come after it. Okay, any other questions? So sometimes these question and answer sessions are short. No one has questions, and that's fine. So they'll take less than an hour. I haven't had them go longer than an hour, but if need be, we have 3 hours of, or 2.5 hours of class time. So we can take that time. But like I say, usually they're relatively quick. Okay, so we will be meeting next week in person, and so you have some time. Let's see. Okay, there's one other question about proof of work from lecture 11. So let me take some time to go through this. Okay, so proof of work is a protocol that you do that is only designed for one function, which is one purpose, which is basically to slow you down. So it's meant to delay you. It's meant to be a function that takes a certain amount of time. It takes a certain amount of effort in order to solve it. And since Bitcoin came out, there's a related concept where it's really geared towards a time delay. In this case, it's more of a resource delay. And so there's some subtle points there. If you want to do a project on the related concept of verifiable delay functions, you can get into the differences between the two of them. But just to keep it more high level, we'll think of it as a time delay. Okay. So for example, let's say I go to you and I say, here's a number, I want you to hash it. Okay, you can hash it and your computer can do that really fast. Okay, it can, it can do thousands of hashes per second, even faster than that. It can do it in a couple of clock cycles. Okay, but what I could do is if I want to slow you down, is I could say, okay, I want you to hash it 1,000 times, meaning like hash it once, take that output and put it as the next input. So you take a value, you hash it, you get a new value, then you're going to hash that new value to get another value, and then you're going to hash that value to get another value, okay? And if I say do that 1,000 times, then now it's going to take a little bit of time, okay? Now I might have to ask you to do it 10,000 times or 40,000 times or something like that for you to even notice it because your computers are so fast. But if I make that number big enough, then there's no way that you can compute that function in any less than a second or 5 seconds or 30 seconds or 5 minutes or whatever sort of time delay that you want. Okay, and so we call this a moderately hard function, and that thousands is a parameter that you can tweak. So you can tweak it to whatever you want. And what will happen is people actually use this, like if they store passwords, they're worried about their password lists being leaked. And so what they'll do is they'll hash it like 1,000 times. And so every time you go to a website and you put in your username and then you put your password in, it takes a while to log in because the server has to hash it 1,000 times in order to match it to what's in the database. But if the password leaks, the hashes of the passwords leak, then if an adversary wants to guess and says, I wonder if anyone in this list has dog as their password, they'll take the word dog. Now they have to hash it 1,000 times, right? So it takes, let's say it takes a second, right? And then they can go through the list of passwords and see if that matches. Okay. And so if they want to go through a dictionary, it's going to take them a long time to go through it because each of these hashes is slowed down. Okay. There were some other ideas of like, every time you send an email, you would have to hash the email 1,000 times, and then it would cut down on spam, because if I'm just sending one email to you, that's fine. It takes me a second to hash it 1,000 times. But if I'm sending that email to 1 million people, and if I have to include, say, their email address in what I'm hashing, then I would have to spend a second to send it to one person, another second to send it to someone else. And I couldn't send it to, or if I send it to 1 million people, I'd have to spend 1 million seconds. And so it would be expensive to me as a spammer. Now there's problems with that too, because there's legitimate reasons, like you send things to mailing lists and things like that. There's legitimate reasons why you would want to email a lot of recipients. But anyway, that was one of the original purposes of it. And there was some other stuff that we talk about in the lecture. Okay, so proof of work is a very simple kind of puzzle. You can think of it as this sort of hash 1,000 password. The actual puzzle is slightly different that will be used in Bitcoin. But the puzzle just takes in a time parameter and it takes in a message. Okay, and it spits out a solution. And the idea would be if I change the message, then the solution would be different. So every different input has a different solution. Okay, and the other thing, this is important, is let's say I ask you, hey, every time you send an email, I want you to hash it 10,000 times, and to prove that you spent some time constructing this email. Just give me one second. Sorry about that. So the password, you would have to hash it 1,000 times. If I ask you to do that, when I get your email and you say this is the email hashed 1,000 times, how do I know that's even right? What I would have to do is I would have to take the email, hash it 1,000 times, and then compare the two in order to make sure that they're the same. Okay, so what we would like instead is we would like a very quick verification. So if someone comes along with a solution, I don't have to redo the proof of work to understand that you did it right. So if you tell me the solution, I should be very easy, like it should be instant for me to check that, yes, this is the right solution to this particular puzzle. Okay, so when I receive a proof of work, I know the definition of the puzzle. I know delta T. You're telling me what was the input that you ran the puzzle on, and you're telling me what the output of the puzzle is. So I'll take your input, I'll take your solution, and I will run a very quick function, and it will just tell me, yeah, that's a correct solution, or that's not a correct solution. Okay, so then what I'll do is I will, okay, so then we can work through an exact example of it. And I'll go through this quickly because it is covered in the lecture. I don't want this to just repeat. I don't want to just give the lecture again. But anyway, so there's one way of doing it, which is what you do is you start with a message, and the challenge to you, okay, so the solution that you're trying to find is you're trying to find a second number, and it can be any number you want, such that when you hash the message with this random number, a hash basically is random. So if I hash something, it will just come out looking like a random number. And the challenge is I want the output to be a very small value or a value with a lot of leading zeros. Okay, so for example, let's say that if I want to do this in real life, so I'll start with the message. So I have it. So the message is kind of like a challenge. Okay, maybe I send it to you. So it's like the email message that you're trying to prove work about. Okay, so you write an email to me, and then you take the hash of my email and you just start with a random number. Just start with 0. Think of it like a counter. So you hash it with 0. And you look at the output will be 1011, blah, 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 right? And you'll say, does that have 10 leading zeros? And the answer is probably not. Okay, so then what you'll do is you'll hash it with the number 2 instead. So the hash of the email with the number 2, does that have 10 leading zeros? The answer is probably not. Then you'll try 3, you'll try 4. And eventually, probabilistically, by statistics, you will eventually try enough random numbers, your counter will go high enough that it will just happen that one of these things will come out with 10 leading zeros. Okay, so let's say it happens at 5,329. Then you'll send that to me. You'll say, here's my email. Here's the number 5,329. And what I'll do as the recipient is I'll just hash those two together and I'll look at the output and I'll say, yeah, that output has 10 leading zeros. And there's no way that you could have known that that would be the number, right? That 5,329 would be the right number because these hashes are random. There's no way that you would know that that would be the right number to give you the 10 leading zeros. So the only way that you found that number is because you tried 0, 1, 2, 3, 4, all the way up to that number. And so I'm satisfied that you must have done, thousands of hashes in order to find that number. Okay. Now, in reality, that number is going to be a lot bigger than 5,000 for 10 leading zeros. You can work out the math. It would be like 2 to the 10, maybe 2 to the 9, because you would expect to find it in half of the time of your search space. But anyways, those are small details. Yeah. So anyway, that's the intuition of the proof of work. And then there's a bunch of math here as well. And so anyways, go back, watch the lectures, hopefully with that intuition that it makes more sense. And if you have more specific questions about the analysis, I can cover them now or next time as well. So just a follow-up is that you do control, so the delta T value that you control. So in this exact example, if you ask for 10 leading zeros, that's going to be harder than if you ask for 2 leading zeros. If you ask for 1 leading zero, half of the time you'll get 1 leading zero. If you ask for 2 leading zeros, it will be 1 in 4 chances. And so this number is a parameter, you control it. It's like a delay parameter. And the higher you make it, the longer it's going to take someone to solve this problem on it. And then the question is, yeah, so a leading zero and a small number is sort of, they're just the same thing. So you can think of it either way. Like a small number is just a number that has a lot of leading zeros, right? Like 0003, if you're thinking of a 4-digit number, it's a small number, it's less than 10, and it has leading zeros. Okay, there's a question about what's the difference between public key generation and a hash function. So this is nice. So they both look exactly the same. So let's see. Okay, I'll just explain it in words. I won't find. This is the public key generation. Okay, so I understand where this question's coming from because structurally they're exactly the same. You have an algorithm, it takes exactly 1 input, it gives you 1 output, and if you look at the output, you can't figure out what the input is, right? Now, the short answer is they're actually the same. So you could argue that a key generation function, especially the kinds that are actually used in signatures, are hash functions. Okay, so then another question would be, well, why don't you just use, why do we have hash functions? If we can do this, why don't we just use this instead? Or if we have hash functions, why don't we use a hash function instead of using this? Like, why aren't they interchangeable? Okay, and so the answer is that keygen is slower than a hash function, but there's some, but it lets you sign things with it. So the output here isn't completely random. There's a mathematical relationship between the public and the secret key. It's a hard relationship that's hard to invert. Okay, so it's based on some known hard problem in math, but there is a mathematical relationship, and that's actually what lets you sign messages. Okay, you're going to use that mathematical relationship so that that when you sign with your secret key, someone else can verify it with your public key, because there's a mathematical relationship between the two. Okay, so you can think of key generation as a hash function with additional sort of mathematical structure that lets you actually do a signature. Now, why don't you just use this instead of a hash function? And the answer is it's slower. So you could, it's like a hash function with this extra feature. So why don't you just use it all the time? The answer is just that it's slow, and it's not that slow. Like we're talking about 100 milliseconds versus even less than that, like 1 millisecond versus 100 milliseconds or something like that. Okay, so but anyways, the point is that a hash function, just there's no mathematical relationship between the input and the output. It's super fast. It's 100 or 1,000 times faster than doing a key generation, and so that's why we have two primitives. So we have a fast one with no mathematical structure, and we have a slow one with mathematical structure. And for signatures, we need that structure, so we can't just use a hash function. And then for everything else where we don't need that math structure, we might as well use the fast version, which is the hash function. Okay. From lecture 2, when you're talking about the hash of a file and comparing it, okay, so this is BitTorrent. Yeah, so the answer to your question is yes, but I'll just explain it. So when you download, for example, a text and you have the hash of a text, you do compare them. So the notation is a little fuzzy, but the hash of file.text ! equals y prime. And y prime in this case, it's the thing that you receive from Alice. So you have a local copy of the file, you hash it, and then you compare it to y prime. Now in BitTorrent, it's a little different. It's basically the same thing, but what you're downloading from BitTorrent is you're getting the file from one place. So the network, all the peers that you don't trust, you don't know who they are, they're giving you the file itself. So you're holding the file in your hand. And what you're getting from the Pirate Bay or from some other tracker is you're getting the hash of what that file should be. So you get the hash of it, which comes down from the Pirate Bay. So they just send you a small value and they say, go out on the network, download the file, and then when you're done, hash it and make sure it equals this value. If it equals this value, then it's the right file. If it doesn't equal this value, then it's possible that one of these peers stuck something malicious in it, or there might have just been corruption or whatever. So yeah, so there is an explicit comparison step. Before you open that file, you better check that the hash that you received from your tracker is equal to the hash that you take over the file itself. So this hash of file here, this is a hash that I computed locally over the copy of the file, which I just completed downloading, and I'm checking it whether it matches the thing that was given to me. Okay, and then there's a question of how do you know which chunk is malicious? So if you take the hash over the whole file and you compare it to this, and let's say it doesn't hold, okay, then you know something went wrong, but you don't know where. Which chunk did it happen in? Where, you know, is there 3 malicious chunks or is there just one? You know, how do you recover? And you don't want to just go and download the whole file again, right? You would like to drill in and do it. So at a high level, this scheme, if you take a hash over the whole file and you get a hash over the whole file, you cannot identify which chunk. All you can do is you can re-download the whole thing and then try it again and keep trying until you get the right thing. But the protocol itself is they don't send, it's not as simple as this. So they're not going to send you just a hash over the whole file. What they'll do is they'll give you hashes over different parts of the file. And so you'll have a bunch of hashes and then you can use it to narrow it down. And then what they can also do is you'll see it later because Bitcoin uses it, but there's this thing called a Merkle tree. And so what they can do is they can put all the different chunks that you're downloading into this Merkle tree. and then that can help you. It can help you find the particular chunk that's wrong. Another thing that it can do is you can go back to the Pirate Bay too and get more information if you need to like try and do a binary search and try and find out which file is malicious. But generally you're basically, the end of it is that you're downloading more than a single hash. You're downloading a collection of hashes in a kind of data structure, and it's going to help you narrow down which chunk is malicious. So I didn't cover all of those details. It was more to give you just the high level, but that's how BitTorrent would work. Let's see. Okay, so a question on signatures is, so here, why are you signing your secret key? And so this actually, the notation is kind of weird. Some people use different notation to sort of distinguish this. These are the parameters that the signature algorithm takes. So it takes the message to be signed and it uses the key to sign it. So you're not signing the message, the key, and the randomness. You're signing the message using the key and the randomness. So sometimes people will put like a semicolon between them, or they might put SK and random as like kind of a subscript here to indicate that it's an input to the protocol, but it's not what you're actually signing. So anyway, so these are inputs to the parameters, but they're not what you're signing. You're only signing the message itself. So you sign the first parameter with using these two as sort of helper values to help you do that signature. Okay, yeah, and then people are identified by their public key. So no one gets a copy of your secret key except for you. You're the only one that knows it. So you advertise your public key. You use your signing key to sign it, but the signature doesn't leak your private key. So when I look at this value, I can't figure out what these two inputs are. They're hidden when I'm looking at this value. And generally the message is hidden as well, although it doesn't need to be, because you always show up with a copy of the message and the signature. But just the way that signatures happen to work is this tends to hide the message as well. Sometimes people deliberately design signatures so that you can recover the message just from the signature, but anyways. Okay, and then there's a question about something I said. So I see the question. It's about something I've written. I'm just trying to find the where I wrote it. Okay, I don't see the part itself, but signatures are they're not encryption algorithms, so they're not meant to hide the message that you're signing. So if you want to use a signature and you're like, I'm going to sign a message and I'm only going to reveal this value, that's, you know, the signature is not supposed to keep the message a secret. It might happen to do it for some signature algorithms, but in general, there's no guarantee that if I only have this value, I can't figure out what this input was. Okay, they're not meant to hide it. They do hide these values. Okay, so absolutely, if you're looking at this, you should not be able to get any information about what the secret key is, but they're not designed to hide any information about a message. So when we think about security, sometimes we contrast integrity and confidentiality. So confidentiality is you have a secret, you want to keep it a secret. There you need things like encryption algorithms. Encryption is not part of Bitcoin, so that we don't cover it. But encryption is the thing that you would use to keep your secret secret. Integrity is I send you a secret, or I send you a message, actually not a secret. Like say I say it over a public channel, and when you receive it, you want to make sure that it didn't get changed. So what I said is the same as what you received. That's integrity. So a digital signature would provide integrity. So I could send a message and I could sign it, and then you could be sure that no one in the middle changed the content. And then sometimes you want both, right? So like right now, where if you see the lock that's on this website, that means that you have both. You have no one's changing the data as it's going across, and it's also seeing the secret as well. Okay, other questions? Okay, so seeing none, that's great. And like I say, yeah, try it if you try and catch up on the lectures if you've fallen behind. And next week we'll meet in person, and we'll do another session like this where you can ask me any questions from the notes. Okay, have a good week, everyone. Take a look at the assignment. You can ask me questions about that as well next week. All right, bye.